previous weeks. So mine is right behind them. Yes, this one, I'm sorry, resource adequacy. Good. Yes.
Hi everyone, we have two presenters today. First one is Mariola Ndrio. She graduated with a BS degree in electrical and computer engineering from National University of Athens in 2014. She got her master's in ECE from UIUC in 2016. She interned with Mid-Continent and New York ISO for 2 summers in 2015 and 2016. And now she is working towards a PhD degree in UIUC with a focus on electricity markets. Mariola.
Okay, thank you very much, Enver. Welcome, everybody. In this presentation today, I want to share with you a very interesting study that we did at the New York Independent System Operator in the summer of 2016. For most of us, we know that the New York State has set some very ambitious goals to go to 50% renewable penetration by the year of 2030. So the goal of our studies was to investigate how the resource adequacy of the electricity grid of the state will be impacted by this high integration of renewable energy resources. For those of you who, okay, can you switch? This is not working. Okay, thank you. So for those of you who don't know, resource adequacy is a term that pertains to bulk power systems, and it's used to describe the ability of the electricity grid to supply the aggregate electricity demand and total energy requirements to all customers at all times by taking into account scheduled but also unscheduled outages in the system components, like, for example, scheduled maintenance in generation units or even random failures in generation units. So how do we measure and how do we perform these resource adequacy studies? In these studies, we are mainly interested in situations where the total firm load obligations in the system exceed the total available generation capacity, resulting in the involuntary curtailment of electricity supply to end-use customers. And we typically refer to these situations as loss of load events. So the RA studies are typically centered in looking into these so-called loss of load events, and more specifically, given a specified time period that, because resource adequacy pertains also to the planning regime in power system operations, we are typically looking into a period of days, months, or even years. So given a specified time period, given a specified model for the demand during that period with a specified time granularity, and given a model for the supply resources, what we are interested to evaluate is what is the probability of these events occurring during that period, what is the expected number of these events, and what is also the total energy not served due to insufficient available installed capacity in the system. And all these things that I just mentioned are the most widely adopted metrics that we use today to measure resource adequacy, and we call them the loss of load probability, which is a unitless metric, the loss of load expectation, which is measured typically in days per years, loss of load hours, which is measured in hours per year, and the expected unserved energy, which is measured in megawatt hours per year. The loss of load, the LOLE and LOLH, the LOLH is the hourly counterpart of the LOLE. Both of them are expectation indices. It's just that there's a small nuance in the way that they are evaluated. The LOLE requires or assumes a daily time resolution for the demand representation, while the LOLH assumes an hourly time resolution, and more specifically, the LOLE models demand, each daily demand value is equal to the daily peak load value, which means that I take the peak value for each day and I assume that it pertains throughout the 24 hours in the daily period, while for the LOLH, I have one separate value for each hour of the day, need not be the peak value. Now, the most widely adopted criterion, these are the metrics, the most widely adopted criterion for resource adequacy today is the ubiquitous 1 day in 10 years, which essentially requires that electric power systems maintain sufficient generation capacity and demand response resources such that the total load in the system does not exceed or maybe exceeds the total available supply no more than once in any 10-year period. Typically, the 1 day in 10 years is expressed as an LOLE value less than or equal to 0.1 days per year. So it's like an upper bound, it's like a threshold that we wouldn't like to exceed. Although there does not exist a rigorous explanation why this is the appropriate criterion in order to set reliability targets and calculate reserves margins in the bulk power system. And although it is not set as a de jure reliability criterion, the 1 day in 10 years is so well entrenched in the electricity industry today that it has become a de facto accepted minimum level of reliability in North America. And in this presentation, I'm also going to assume that whenever my system satisfies the 1 day in 10 years criterion, then I have a resource adequate supply. And whenever it violates the criterion, then I have a resource inadequate supply. So why resource adequacy has become so important? Well, the basic reason is because the resource mix is changing. And over the last decades, we have all seen that deepening renewable energy penetration in electricity grids around the world. In this map, I'm showing some key events that have occurred during the last years. I was very impressed by the fact that in July 2015, high winds in Denmark were actually sufficient to supply the total demand in the country only from wind generation, with enough to share for Germany, Sweden, and Norway as well. In February 2017, the SPP was able to supply 52% of its electricity demand only from wind resources. I mentioned in the beginning that the New York State has already set targets for 50% renewable penetration by 2030. California also has set similar targets. The European Union has set a target of 27% penetration by 2030, with individual countries like Sweden setting targets as high as 49% for the 2030 year. So what is going on is that new resources are coming into the grid, and the key thing is that these new resources have different reliability characteristics than the resources they displace. So the fundamental question is, as we move from polluting but yet with low outage rates conventional generation resources to cleaner but yet intermittent, highly intermittent with variable output resources, are we still going to have a resource adequate supply system, or what's happening to the resource adequacy of the system? And that was exactly the question that we tried to answer at the New York ISO. This was our study system, the New York control area. The state has most of its generation resources are located to the northeast and northwest, while the load is mainly around the New York City, at the south of the state. The projected summer peak demand for the New York for 2030 is 36,800 megawatts. The total installed conventional generation capacity, and that includes also imports from the neighboring region plus hydro generation, is approximately 40,000 megawatts. The penetration from hydro right now is approximately 25%. There are some solar and wind resources installed in the NYCA, which are approximately at 5% penetration. So we performed two distinct set of studies. In the first set, we added solar and wind generation resources into the NYCA, into the existing fleet of conventional generation resources. Our maximum installed solar capacity went up to 4,000 megawatts, and for wind, 15,000 megawatts. In total, that made a 25% penetration from solar and wind, which from the 25 penetration from hydro amounts to the 50% penetration that we want to achieve by 2030 from hydro, solar, and wind alone. Now, in the second set of studies, we did something else, like we did not just add solar and wind capacity into the system, but we added them, and simultaneously we retired conventional thermal units, the polluting units from the NYCA. In a few words about the simulation studies, we used actual demand data from the New York control area from the period of 2011 and 2015 for a total of 6 years. From the same period, we used hourly generation output from solar and wind, existing solar and wind plants in the NYCA. There were approximately more than 400 conventional generation units in the system, with including 3 nuclear power plants, with reliability data taken from NERC's generating availability database. We constructed approximately 59 different cases for the first set of studies, where each case corresponds to a distinct pair of solar and wind generation penetration for the system, and 373 cases for the second set of studies, where each case for the second set corresponds not only to a distinct pair of solar and wind generation penetration, but also to a distinct level of thermal capacity retirement. Before I show you some of the results, I'm going to use gamma, superscript S, or W notation to indicate the solar and wind penetration into the system respectively. And the penetration is defined everywhere, is represented everywhere as a percentage, and is defined as the total energy produced from solar resources for a specified time period over the total energy produced into the system. And I'm going to use zeta to denote the retirement factor, which is also defined as the total retired conventional capacity over the total renewable capacity added into the system. So for example, a zeta equal to 0.9 means that for every megawatt of solar and wind capacity that I add into the system, I remove 0.9 megawatt of conventional capacity. So for the first case of studies, Kevin? Yes, where I haven't removed anything. Zeta is equal to 0. I'm going to tell you when zeta is going to be non-zero. I haven't retired anything. I have the existing fleet of conventional capacity resources into my system. What I'm plotting over here are LOLE values in days per year for different scenarios of wind and solar penetration. Every data point corresponds, like I said, to a distinct pair of solar and wind penetration into the system. A couple of observations which are important is that even at the case where I have 0 wind and 0 solar penetration, the LOLE value is approximately 0.06. That is well below the threshold that I mentioned to you before, the 0.1 days per year. So I have already a resource adequate system. Of course, it's intuitive to see that the LOLE values are decreasing as both wind and solar penetrations are increasing, because you're adding more capacity into the system. So you expect that you are doing better in terms of the reliability of the system. However, the marginal returns from the reduction on the LOLE are diminishing as you increase both the solar and wind penetration. That means that when I'm adding 1 megawatt of solar capacity at a 0 solar penetration, the impact of that megawatt is going to be much higher than when I'm adding 1 megawatt of solar capacity at a 10%, say, for example, solar penetration. However, I think that the most important outcome that came from our study is that the impact from solar resources was significantly higher than the impact from wind resources. Yes, you can click that, because I want to show those 2 data points. No, previous. No.
How do I get previous list?
And another one. There you go. So I have circled those two data points because the point on your left, it corresponds to a scenario where wind, I have a 20.06 wind penetration in the system and 0% solar. And the LOLE is a little bit higher than 0.02 days per year, while the data point on the right corresponds to 0 wind penetration and solar a little bit higher than 2.2%. And again, I have approximately the same value on the LOLE index, which means that it took me 20.06 penetration for wind, or 15,000 megawatt of installed wind capacity, to reduce the LOLE approximately at the same level than 3,000 megawatt of solar capacity could do. So it appears, and overall, throughout the entire results that we got, the impact from solar resources were an order of magnitude higher than those from wind. And the reason, the explanation for that is that NYCA is a summer peaking unit. And that means that the hours or the days of the year of the study period that contribute the most to the probability of a loss of load event and to the expectation of a loss of load event are those where demand is reaching or is very close to its peak value. So that is when, so it appears to be that solar output has a higher correlation with demand as respect to in comparison with wind resources, which appear to be much more have an anti-correlated behavior with demand. So more specifically, although I have added so much wind capacity into the system, if the output of the wind resources is very small or insignificant during the hours where demand is very, very high, then their contribution to reducing the loss of load probability will be very small. Okay, this is what this is simply what it's telling us. Yeah.
So for each of these data points, how are you evaluating the loss of load?
I didn't want to get into the details of that because it will take so much time. So we have a certain demand profile for 2030, 8,760 values. Okay, we have solar and wind resources, our yearly profile for each of them. Again, hourly values. In order to incorporate them, we subtract them from the demand in order to get the net load. For resources which are not renewable, like solar and wind, but are thermal resources, we have forced outage rates, like probability that the resource will be out of service and probability the resource will be operating. So those are modeled like, in most of times, as a three-state Markov, as a three-state unit, with probability of transitioning from one state to the other. So essentially, what we did is that you construct from the combination of all the generation of the thermal resources, not renewable, from the combination of all thermal resources, all the possible capacity states, and you compare them with all the possible demand states. And for every hour where the available supply is strictly less than the hourly net load demand, then you count that hour as a loss of load event. And in the end, you collect all the statistics, and from the statistics, you construct the LOLE, the LOLH, and so forth.
Is it fair to say the ramping constraints will become?
No, not so much.
The reason I'm asking, in California, that's one of the things that people are worried about, the duck curve, right?
Yeah, no. Yes, this is much more on the planning. Yes, not so much on looking at the short-term operational movement. Yes, yes, that's correct. Yes, Kevin, you can go on. The similar outcome was for the loss of load hour index. Again, it's reducing, diminishing marginal returns, solar, much more impactful. The same for the expected unserved energy. Now for this is the next slide. For the expected unserved energy, there are a lot of people who advocate that we should move from having a reliability index expressed in days per year to something that is expressed in megawatt hours per year, because it is much more meaningful to say that I had over this time period, I wasn't able to serve like 100 megawatt hours throughout the entire study period, than say I have a loss of load expectation 0.1 days per year. In the end, what does it mean? Okay, so you can go to the next one. So now where we started retiring conventional generation capacity, I'm sorry about this, but I've changed the diagrams a little bit. I'm using the vertical axis to show wind penetrations and the horizontal axis to show solar penetrations. Every data point corresponds to an LOLE value for a distinct pair of solar and wind penetration and a distinct value of zeta. So zeta here is 0.25, which means that for every megawatt of solar and wind, I have retired 0.25 megawatts from conventional generation capacity. I'm not so much interested to show you what is the exact value of the LOLE. I just want to show you that the increasing sizes of the circles indicate increasing values of the index. And I want to show you also which are the scenarios that will take me up the threshold, the 0.1 threshold. So for this case at 0.25, I have plotted only a few representative of them because we ran far too many cases. The only scenario that took us a little bit higher than the 0.1 threshold is when the system has installed zero solar and it has approximately 30% penetration of wind, which means 15,000 megawatt of wind installed capacity, but which also means retired 3,750 megawatt of conventional generation capacity, which means that wind is not helping me almost at all to reduce it's actually exacerbating. Go ahead. And if I want to increase zeta even more, even the ability of solar, which is so beneficial for this system, starts to become limited after I start increasing the retirement factor. And if I go to even 0.5, I will start getting the majority of the scenarios were below with the LOLE higher than 0.1. And if I go to 0.9, which after some point it made no sense to run any more scenarios because we were getting so ridiculously high values for the LOLE, but just to give you an idea, the worst of the scenarios we got was 0.9 retirement of conventional capacity and approximately 26 to 27% total solar and wind penetration, which gave an LOLE of 6.22 days per year, which is unacceptably high. But that scenario, just to give you an idea, we have added 90,000 megawatt of solar and wind, but at the same time, we have retired more than 13,000 megawatt of conventional generation. Okay, so everything is very nice. We can add solar and wind resources as much as we want, as long as we as long as we keep intact the existing fleet of conventional generation capacity. Solar for the New York system has much more impact than wind resources. However, the resource adequacy of the grid begins to deteriorate drastically once we start taking out the highly reliable polluting but highly reliable conventional generation. Can go to the next one. Once we reached above the 0.25 retirement factor, we began to have the majority of the cases where for an LOLE higher than 0.1, which highlights the care that grid operators must exercise when it comes to retiring these polluting thermal units. Okay, thanks. That was the end.
Thank you, Mariola. Do we have any questions? Maybe we can have one or two.
Yes, Essie.
You mentioned at the beginning the 1 day, 10-year concept, which is a big part of your final conclusion. Do you have a personal idea on what a better, because you said that it's so ingrained?
Yes. That is something very interesting. A lot of people are trying to, like NERC is very much encouraging to move away from that. They are looking into having a reliability criterion expressed in terms of the expected unserved energy instead of days per year. I don't know what would be actually. That is a very tough question. And I think that what is the most impressive thing is that nobody wants to move away from it for some reason. Like people believe so much in it and have adopted for so many years, and nobody is willing to question it in some sense. So it's very, very widely adopted. Although I'm telling you again, it appeared actually, they told us that it appeared in a paper from Calabrese in the 60s. And somebody just suggested, let's keep an LOLE below 1 day in 10 years. Let's keep the system not to have more than one event in a 10-year period. And that's how it started. It dates back to the 60s to a paper. That's when it appears. It appeared the first time.
Thank you, Mariola.
Okay, thank you.
Let's see if that's gonna work.
Yeah, let's just, that's fine. Yeah, look, you want to just use this one? That software's already loaded.
Okay.
How can I go to the forward, reverse, the legs are pointing out?
This is just for the recording.
Okay.
It's an empty file.
Okay.
All right. Our second speaker today is Hyungjin Choi. Sorry. Mr. Choi received the PhD degree in electrical engineering from University of Minnesota in 2017. He's currently a postdoctoral research associate in the Department of Electrical Engineering in Professor Bose's research group. His research interests include the application of numerical optimization and control theory in modeling, analysis, and operations of power systems.
Thank you. Thank you for coming to my presentation today. My name is Hyungjin Choi. I'm a postdoc working with Professor Bose. Today I'm talking about the power system analysis with uncertainty. So there are two main topics in this presentation. First, I'm going to propose an analytic method to quantify how the bounded uncertainty set can propagate along the solution of the power system model. And in the second topic, I'm going to present the estimation of stability boundary of power system dynamics with given bounded uncertainty set. So the motivation is that there are increasing number of uncertainty variables in the power system, including some of the parameters or renewable generation or the elastic loads. And those sources of uncertainty can introduce the challenge in the reliable and stable operation of power systems. So it is important to develop the algorithmic method to quantify the impact of uncertainties. So in this slide, I'm going to briefly go over the power system model and power system and uncertainty model that we adapt throughout the analysis. First, any given power system can be described by the differential algebraic equations, where the x, y, and u are the differential algebraic and uncertainty variables. And also we adapt the unknown but bounded uncertainty model, which means that the variations in u, which is delta u, is upper and lower bounded by u mean and u max around the nominal value of the values of u, which is the u bar. So the first topic is uncertainty propagation. So this is the proposed framework. So regardless of the size of the system, the power system can be described by the DA model. And our goal here is to estimate what's the maximum and minimum bounds on all possible values of states given the bounded uncertainty set. So as a first step, we need to derive a new set of differential algebraic equations defined as sensitivity equations. So the solution of this equation gives you the information on the linear and quadratic sensitivity on the variation of a state with respect to an uncertainty variable u, which is defined as the sensitivity variables. And with the values of those sensitivity variables, we can construct the quadratic approximation of a state by using the Taylor series approximation up to second order with respect to U. And we can formulate non-convex quadratic programming to estimate what's the minimum and maximum bounds on a state given a bounded uncertainty set. So in the quadratic approximation of a state, the second term and third term captures the linear and the quadratic sensitivity information on the variation of a state G with respect to the variations in U. As we can see from the entries of this Jacobian and Hessian matrix, which is the first order, second order, and mixed partial derivatives of our states in terms of U. So we define those variables as the first order, second order, and mixed sensitivity variables. And to get those values of those sensitivity variables and then populate the Jacobian and Hessian matrix, eventually we can construct the quadratic approximation of a state. To do that, we need to derive a new set of differential algebra equations called sensitivity equations by taking partial derivatives of the original differential algebraic equations of our power system model. So then we can formulate the problem of estimating maximum and minimum bounds on a state given a bounded uncertainty set as a non-convex quadratic programming by putting the quadratic expression of our state as our objective function and the bounded uncertainty set as our constraints. And this problem is non-convex problem because we don't know a prior guarantee of the positive or the negative semi-definiteness of the matrix H. So we approach this problem using the typical semi-definite programming relaxation, where first we are reformulating the original QP problem in a quadratic form with the monomial vector 1 and U, and then matrix M and C by equating all the coefficients of the objective function and the bounded uncertainty constraints with the entries of M and C. And without too much mathematical details, following the typical SDP relaxation technique, we can end up having the two SDP problems for lower bounds estimation and upper lower bounds estimation. And we can also use the ADMM algorithm to solve this non-convex QP problem by first formulating the original problem as a consensus form by introducing the new primal variable G, substituting the uncertainty variable U in the constraint, and then adding the consensus equality constraints U equal G. And then again, following the same the typical ADMM algorithm that solved the three update problems iteratively with the given augmented Lagrangian function. So the algorithm that is guaranteed to converge to a stationary solution satisfying the KKT condition if the problem satisfies the three assumptions. First, the objective function of the QP should satisfy the Lipschitz continuity of the gradient Lipschitz continuity. And the rho, our augmented Lagrangian multiplier rho is chosen large enough so that its update problem is strongly convex. And then our objective function G is bounded from below. So we implemented this method for the New England test system where there's 10 synchronous generators and 39 bus divided into area 1 and area 2, governed by the automatic generation control and area control error. So the power system model in this case includes the dynamics from the synchronous generator, automatic generation control, as well as the power flow balance equations. And for this case study, we introduced uncertainty for some of the parameters and inputs, including the economic dispatch signal for generator 4, the damping coefficient constant for generator 8, and then load real power at bus 25. And here are the results of our proposed methods. So estimated upper and lower bounds, where the red and blue curves are the upper and lower, estimated upper and lower bounds. And in between, there's the green curves, which are from the repeated time domain simulation for randomly sampled values of uncertainties. So we can see from here that our proposed method can estimate the upper and lower bounds accurately. So the next topic is the robust stability analysis. So this is the proposed framework. So again, given the power system, we're given the power system, and in this case, we assume that we can model the power system as a dynamic polynomial differential equation, which is x dot equal px u. And for computational feasibility of our analysis, we further approximate this polynomial vector field as an affine function in U. And our objective is to find what's the stability boundary of our dynamic equation that capture all initial points, capture all stable initial points given a bounded uncertainty set in the system. So the Lyapunov stability condition gives you the certificate for this ROA, and we can formulate the problem of estimating the maximum sub-level set of this ROA as a sum of squares optimization problem, especially given the bounded uncertainty set. So ROA is the set that captures all. ROA is the set that captures all stable initial points. The more descriptively, if you start from the inside of this boundary, it's going to converge to the stable equivalent points. Otherwise, it's going to diverge. It's unstable. So the Lyapunov stability condition states that given the dynamic system x dot equal p, if there exists the positive function v such that v is bounded by gamma, and then gradient of v is negative along the dynamic vector field, then this set that v is bounded by gamma is a sublevel set of the exact ROA. So our objective is to find what's the maximum sublevel set of ROA. So that problem can be satisfying the Lyapunov stability condition. So that problem can be casted into the sum of squares optimization problem by using the definition of sum of squares function. So the sum of squares function is defined as a sum of all squared polynomials, and it naturally guarantees the positive definiteness of a function. So in the SS optimization problem, we are maximizing a sum constant gamma, which is translated into maximizing the sublevel set of ROA, subject to satisfying all the sum of squares version of all these Lyapunov stability conditions. And this sum of squares constraints comes from the set containment condition where the omega v gamma is actually invariant subset of the exact ROA, which is gradient of v is negative. And if we assume that our power system has some uncertainty in the dynamic model, we need to define the robust ROA. So the robust ROA is a set of all stable initial conditions for any possible values of uncertainty in the bounded uncertainty set. So illustratively, the robust ROA is the intersection of all ROAs for estimated found from all possible values of uncertainty in the bounded uncertainty set. So again, we're trying to maximizing the sublevel set of this robust region of attraction, and this can be also translated into sum of squares optimization problem. Given the polynomial dynamic equation x dot equal p, it is impossible to consider all possible points inside the bounded uncertainty set. Instead, we approximate the polynomial vector field as an affine function in U, so that we can confine our interest, or the point of our interest, as a worst case uncertainty scenarios, which is, in this case, which is vertices of the polytope. So similar to the deterministic case of the sum of squares optimization formulation, we're formulating sum of squares optimization, but in this case we have some more set containment conditions, and each set containment conditions represents its vertex on the bounded set. So we applied this method to the very simple two-machine input bus system, where there's a generator, synchronous generator at the bus 1 and DFIG at bus 2, and the PQ load at bus 6, and then infinite bus voltage at bus 3 connected through the transmission lines. And we introduced some parametric and input uncertainty, including the generation output at bus 1, or transmission line impedance between the bus 3 and 6, and the infinite bus voltage magnitude. And we estimated the robust region of traction from using our proposed method. And here, red curve is the robust ROA estimated from our proposed method. And the blue curves are the ROAs estimated from the randomly sampled values of uncertainties. So from this, the result, we can see that the robust ROA is truly the intersection of all the ROAs for all possible values of uncertainty. This is, yeah. So we discussed about. So in this presentation, I discussed about how given the bounded uncertainty set in the power system model, how this uncertainty can propagate along the solution of the power system dynamics. And in the second topic, I discussed how we can estimate the robust stability boundary of our power system dynamics given some parameters and inputs that are uncertain in our power system dynamic model. Thank you.
Do you have any questions? I guess we thank you.
Thank you
For your presentation.
Yeah.